Today's numerical is a 50 square bar is subjected to an axial tensile load of 250 kilonewton. Determine the decrease in the lateral dimension if Young's modulus is equal to 200 gigapascal and Poisson's ratio is 0.3. Now first understand question. Understanding question is first step and it is very important step. 50 square steel bar. Diagram for that square steel bar. Steel bar length L and this dimension, lateral dimension is A, and 250 kilonewton tensile load is acting on this bar, this and this side, 250 kilonewton load. Determine the decrease in lateral dimension. See, this A and A is lateral dimension. For that, this x direction is L and L is longitudinal direction. This y direction is this A side, vertical A side, and this Z direction is perpendicular to this vertical A side is also A. This is Z. This y and z are lateral dimensions and x is longitudinal dimension, and we have to determine the decrease in the lateral dimension. That means decrease in A. To find change in A, change in lateral dimension, and given data is 50 square bar. This A lateral dimension is 50 and bar is steel bar, and the axial tensile load P is 250 kilonewton. Determine the decrease in E is equal to 200 GPa, gigapascal, and Poisson's ratio mu is 0.3. This P is 250 into 10 raised to 3 Newton. This kilonewton convert it into Newton, multiply by 10 raised to 3, and this gigapascal convert it into megapascal, multiply by 10 raised to 3. For calculating this change in lateral dimension delta A, we need stress and lateral strain. For finding stress, formula is stress is equal to load upon area. First, stress denoted by sigma is load upon area. This axial load they have given us in numerical. This load is denoted by P and area is denoted by capital A. P is 250 kilonewton. That means Newton, 250 into 10 raised to 3 Newton, and cross sectional area for that, this P load, 250 kilonewton load acting on A multiplied by A cross sectional area, this much. See cursor, this much cross sectional area, this 250 kilonewton load acting. That's why area is 50 multiplied by 50. This y direction and z direction dimensions 50 by 50 is equal to 250 into 10 raised to 3 upon 50 into 50 is 100 Newton per mm square. unit of stress is Newton per mm square, or you may call it MPa, because Newton per mm square is equivalent to MPa. 1 Newton per mm square is equal to 1 MPa. Next, to find linear strain. Linear strain is denoted by E, and to finding linear strain with the help of Young's modulus formula, we find linear strain, and Young's modulus formula is E is equal to stress upon strain. Therefore, this linear stress upon linear strain, and with the help of this formula, this small e linear strain is equal to stress upon Young's modulus. Why we find this stress? Because here for calculating linear strain we need stress. That's why I find this stress, and the stress is 100 Newton per mm square. 100 Newton per mm square divided by this E Young's modulus they have given us in numerical. E is 200 into 10 raised to 3 MPa. 200 into 10 raised to 3 MPa. And linear strain have no unit, but see, this stress unit is Newton per mm square, and this Young's modulus unit is also Newton per mm square. Newton per mm square, Newton per mm square get cancelled. That's why here strain have no unit, and linear strain comes 5 into 10 raised to minus 4. See, we find this stress, and with the help of stress we find linear strain. Now with the help of linear strain we find lateral strain. We will find lateral strain. With the help of this linear strain we will find lateral strain. And for finding lateral strain we use formula of Poisson's ratio. See, first lateral strain, and our main objective of this question is finding lateral strain. See here they have tell us to determine the decrease in lateral dimension. Lateral strain, this is our main objective, to finding lateral strain. And with the help of this Poisson's ratio mu formula, mu Poisson's ratio is nothing but the lateral strain to the linear strain. And with the help of this formula, see here lateral strain, therefore lateral strain is equal to mu into E. And this mu they have given us in numerical, mu is 0.3, and E we find last step, C 5 into 10 raised to minus 4. Here for calculation of lateral strain we need this linear strain. That's why here we first find linear strain 5 into 10 raised to minus 4. 5 into 10 raised to minus 4. Therefore lateral strain is 0.3 into 5 into 10 raised to minus 4 is equal to 1.5 into 10 raised to minus 4. This is the lateral strain, and they have given us a numerical, determine the decrease in lateral dimension. Sorry, here they not ask us lateral strain. See, I write here main objective, I tell you that our main objective is lateral strain, but see here, observe here, determine the decrease in lateral dimension. They ask us decrease in lateral dimension, they don't ask us lateral strain. For that, decrease in lateral dimension, that means change in lateral dimension. Strain is change in length upon original length, and lateral strain is change in this lateral dimension to the original dimension. So with the help of this lateral strain, see here, change in lateral dimension. Our procedure is correct, but only our objective is this. Main objective of this question to find is this change in lateral dimension. And lateral dimension is A and change in lateral dimension is delta A. Lateral strain is equal to change in lateral dimension to the original lateral dimension. Therefore, this delta A is equal to EL into A. Basic mathematical, with the help of basic mathematical calculation, we find change in lateral dimension EL is equal to, sorry, delta A is equal to delta A is equal to EL. See, this is EL 1.5 into 10 raised to minus 4 into A is 50. See, this lateral dimension A is 50 mm. 1.5 into 10 raised to minus 4 into 50 is 7.5 into 10 raised to minus 3 mm. Very less change in lateral dimension is seen. Original dimension of this rectangular steel bar is, original lateral dimension is 50 mm, and after acting this axial force, axial tensile force 250 kilonewton, this this change in lateral dimension, very small change in lateral dimension is seen, and lateral strain is 1.5 into 10 raised to minus 4. Stress is 100 Newton per mm square for this load 250 into 10 raised to 3 load, axial tensile load, this much stress comes. Observe here in stress formula, when we increase area of that rectangular area of that rectangular bar, cross sectional area of that rectangular bar, when we increase cross sectional area of that rectangular bar, there is decrease in stress is seen. Analysis of this problem is, when we decrease this area of cross sectional area of this rectangular bar, stress stress comes more, and when we increase this area of rectangular cross sectional area of bar, stress comes less. See, I write here for study and analysis purpose. See, area, cross sectional area, see, cross sectional area of that bar increases, stress decreases. That means when we increase cross sectional area of that rectangular bar, we indirectly increase capacity of stress gain of this rectangular bar, and cross sectional area decreases. See, this decreases, then stress increases. Therefore, strength of this steel rectangular bar material is depend upon this cross sectional area. As we increases cross sectional area of this rectangular bar, there is stress capacity is stress capacity is, stress acting on this bar is decreases. That means strength of this bar increases. And when we decrease cross sectional area, stress comes on this bar increases. That means this bar have low strength. And after linear strain, see here linear strain, what analysis we have to study. Linear strain is also very small. E is equal to 5 into 10 raised to minus 4. Between linear strain and lateral strain, see difference 1.5 into 10 raised to minus 4, here 5 into 10 raised to minus 4, and our change in lateral dimension is also very small, 7.5 into 10 raised to minus 3 mm. Only solving a problem is not okay for study, is not beneficial for study. Solving problem, see this problem, see answers, analysis of this problem is also very important. Thank you very much.